If your simulation gives wrong vapor-liquid equilibrium, your entire plant design can fail. And in most cases, the reason is just one wrong property package. Today, I will explain one of the most powerful and widely used equation of state models in the oil and gas and chemical industry, the Peng-Robinson property package, where to use it, where not to use it, and why engineers trust it. Hello everyone, welcome back to the Chemical Engineering and Aspen channel. In this presentation, we will thoroughly explore the Peng-Robinson equation of state. We will cover the understanding of the Peng-Robinson equation of state, what is this property package and its fundamental principles, the working principles and operating ranges of this property package, that how it functions and its optimal application conditions, the industrial applications where this powerful model is most effectively utilized, and finally the accuracy and common pitfalls, that where we should use it, where we should avoid it, and accordingly, if you utilize Aspen HYSYS, Aspen Plus, Unisim, DWSim, or any other process simulator, comprehending this model is absolutely essential. So what exactly is Peng-Robinson equation of state? This model was introduced in 1976, called an equation of state, or is under the equation of state umbrella, and is designed to enhance vapor-liquid equilibrium predictions, particularly for hydrocarbon system. It is a cubic equation of state that establishes the relationship between pressure, temperature, and molar volume, and its primary objective is to accurately forecast the vapor-liquid equilibrium, the phase behavior, density of gases and liquids, enthalpy and entropy, compressibility factors. In essence, this property package informs the simulator that how the fluids behave under varying temperatures and pressures, which is again a very critical aspect once we're designing a process. The Peng-Robinson equation of state is widely used, especially for hydrocarbon systems. The power behind the Peng-Robinson, that why it's indispensable. Number one is that it is excellent for non-polar systems, that highly effective for non-polar and mildly polar systems, making it ideal for hydrocarbon applications. Number two, high pressure accuracy, that provides accurate results when we are dealing with the high pressure conditions. Number three, superior critical range predictions, that outperforms older models in predicting the critical region behavior crucial for phase transitions. Number four, the computational efficiency, that it offers computational efficiency, allowing for faster and more manageable large-scale simulations. Understanding the optimal operating range of Peng-Robinson, that once we talk about the pressure, low to very high pressure systems, it has a very wide range in temperature from subcritical to supercritical. Fluid type, non-polar, slightly polar. So it can also handle slightly polar systems, but most widely it is used for non-polar systems. Particularly effective for light hydrocarbons and natural gas systems, refinery streams, refinery processes, and petrochemical industry, oil and gas industry, but it is not recommended for strongly polar compounds, electrolysis or electrolytic system, and hydrogen bonding systems such as water and alcohols. So we have already know these, especially the non-recommendation or recommendation aspects, since we are on this channel from last 5 years. Key industrial applications of the Peng-Robinson equation of state are: number one is oil and gas production, that used in the upstream and midstream operations for accurate phase behavior modeling. Gas processing plants, essential for design and optimization of separation processes, which also includes the LNG, the liquefied natural gas. The refinery simulations, that crucial for modeling distillation columns, high pressure separators, compressors, and pipelines. If your system predominantly contains components such as methane, ethane, propane, butane, CO2, and H2S, that the most preferred property package is Peng-Robinson. What mistakes you should avoid once we are using the Peng-Robinson equation of state, that it is not suitable for highly polar or water-rich systems, so you should not be using this. Binary interaction parameters are very crucial parameters, and ignoring these parameters can result in the drastic results or drastic outcomes. So you have to make sure that binary interaction parameters are available. You should not be using it for electrolytic system as it does not have any characteristic to translate the electrolytic systems. So these misapplications can result in incorrect phase splits, inaccurate energy balances, and ultimately inappropriate or improper equipment over design or maybe under design, leading to costly operational issues. Strategic use: when to deploy Peng-Robinson effectively. Use when the system is hydrocarbon dominant, operating from moderate to high pressures. Phase equilibria is a critical aspect of the simulation, and the application involves gas processing or refining. When should you avoid it? The opposite, which means that strong hydrogen bonding were involved, such as water alcohol system. For electrolytic system, you should not be using it. For highly non-ideal liquid mixtures, you should not be using it. And choosing the correct property package is fundamental to obtaining the reliable simulation results and ensuring process integrity. If we talk about the professional insights of comparing Peng-Robinson versus other models, PR versus SRK, Peng-Robinson versus Sob-Reddish-Pong. Now both belongs to equation of state. Peng-Robinson generally provides superior liquid density predictions. SRK is sometimes more accurate for light gas system. This is just an overview. Obviously, in our upcoming videos, we will have much better description or comparison between these two. Once we talk about the Peng-Robinson versus activity coefficient models, now that Peng-Robinson belongs to equation of state, utilize NRTL/UNIQAC. These belongs to activity coefficient model for polar systems where molecular interactions are significant. Employ Peng-Robinson specifically for hydrocarbon VLE to leverage its strength in non-polar interactions. So you have to, or you must have a clear understanding of which property package to be used when. Going to the last slide of today's lecture, that in environments like Aspen HYSYS, Aspen Plus, selecting the Peng-Robinson property package automatically triggers the calculation of several thermodynamic properties such as Z factor, which is compressibility factor, enthalpy, entropy, fugacity, and phase fraction. This comprehensive calculation directly influences the accuracy of flash calculations, column convergence, compressor duties, heat exchanger duties. Therefore, selecting the correct property package is not only an option, it is our fundamental requirement if we want to get our robust and reliable process simulation leading to correct equipment designs. So to summarize, Peng-Robinson equation of state is best for hydrocarbons, excellent at high pressures, widely used in oil and gas, critical for VLE accuracy, but must be used with engineering judgment. If you want more practical simulation knowledge, like the video, which is related to property package, column design, compressors, reactors, and subscribe to the channel and turn on notifications. Drop your questions in comments and I will reply to simulation doubts. So till then, it's goodbye. Stay tuned for more exciting videos on this channel.